Dr. Elena Rantou is the lead mathematical statistician within the Office of Biostatistics, CDER, FDA, and she will be discussing statistical consideration for assessment of IVPT data for evaluation of BE. Elena?
Thank you, Priyanka, for the introduction. I am very happy to be here. I will start with a disclaimer that this presentation reflects my views and not my agency's views, and also that the data sets shown in this presentation have been previously de-identified. So throughout this talk, I'm going to give an overview of the IVPT data and study design. I'm going to give some background about the development of the statistical analysis for assessing bioequivalence in IVPT data, and also talk about how this method has evolved, and also discuss some issues that arise with IVPT. So IVPT, the in vitro permeation test, uses excised human skin, measures drug concentration, and the rate of drug delivery or flux is measured by sampling at specific pre-selected time points in a way analogous to that used in blood or plasma concentration sampling in PK studies, in pharmacokinetic studies. So this is a slide that you previously saw, very thoroughly explained by Dr. Rani. Here I'm going to just repeat and remind how we have one donor, and from this donor we have replicate skin sections dosed by the test product. So we take one of these and place it in the diffusion cell, and then through the sampling port we get 1 point, excuse me, and we repeat the same thing with a reference product, and also then for a second donor, a third donor, all the way up to n donors. So we construct a pharmacokinetic type profile, flux profile, out of this process. And this graph shows such flux profiles in cases where we have 3 different lots of the same RLT product and 1 test product. So every row will represent a different product, and every column will represent a different donor. And what is important to observe here is that we may have different behavior for one donor comparing to the other donors. However, we have a consistent behavior across, for the same donor, across the different products. So before, we did not have the procedures to perform the statistical analysis to assess bioequivalence, but the developed method uses the approach for the scaled average bioequivalence, which was originally for highly variable drugs, that is now modified for the IVPT study design. It uses a cutoff value, that of the within reference standard deviation. So when this value is less than or equal to 0.294, this value is equivalent or corresponds to a coefficient of variation of 30%. Then that prompts to using average bioequivalence. Whereas when this value is greater than 0.294, we will use the scaled approach. So the results obtained with IVPT and the suggested statistical analysis agreed with the original results that led to the regulatory approval of different products. And this supports the validity of the model for assessing bioequivalence. Also, the test has been used to comparing 2 batches of the same reference product and successfully captured the similarity of these products in terms of bioequivalence. So these outcomes support the model's sensitivity to meaningful differences and its resistance to the hazard of rejecting good products. These observations are depicted here in the next 2 slides, where it shows that for a product and its negative control, the test has been successful to capture the non-bioequivalent relationship between these 2 products. and also when we have a positive control, which we create by having 6 replicates for every donor and dividing, randomly dividing to 3 and 3, so we have a positive control or comparing a product to itself. And this bioequivalent relationship was correctly captured by the test. So these are all from previous research, and also we have looked into the performance of this test in terms of statistical power. So in the graph on the bottom left, we see the superiority of the mixed criterion, the mixed scale criterion, rather than using regular average bioequivalence in terms of statistical power, and also some investigation that has been done in terms of how many replicates do we need to achieve the adequate statistical power. We also have looked into selecting the number of donors for a pilot study. So here, for a specific data set, we have the value of the point estimate and the value of SWR, and here by point estimate, I mean the geometric mean ratio. And assuming that this is the true value, we have applied a bootstrap type of simulation to see how close we come to the true value when we have, we create a distribution having 4, 5, or 6 number of donors. We didn't see dramatic differences, but we saw a constant improvement in precision as the sample size increases. Additionally, we concluded that the choice of the sample size in a pilot study also depends on the characteristics and validity of each data set. So when do we have unbalanced data? Replicate skin sections are withdrawn when samples from the diffusion cell are destroyed. And this is an anticipated experimental event. And there is documented evidence that skin is damaged during the course of the experiment. In such cases, replicate values can be replaced, so there is no informational loss. In situations, however, where we are unable to replace the diffusion cell, replicate values are dropped, but not uniformly for all donors. This needed to be addressed by adjusting the statistical test to account for the situation of the unbalanced data set. So here we see a similar slide to the previous one, where now we see the difference between having a balanced and an unbalanced data set. So in the case of the unbalanced data set, we see some replicate skin sections missing per donor, per product, but not uniformly missing. So we end up not having the same number of replicates per donor, per formulation. So in the balanced case, we have a sample of N donors. We have our replicate skin sections per donor and per treatment. And we have, of course, 2 treatments, the test, which is the generic product, and the reference product. So we will construct the confidence interval for 2 parameters, for 2 endpoints, the natural log transform maximum flux, or the natural log transform total cumulative penetration, or AMP, so which used to be called AUC. In the unbalanced data case, we have one observation, TIJ, being the natural log transform Jmax or AMP, dosed with a test product for the ith replicate from the J donor, and similarly RIJ from the reference distribution. Here, what is different is that we do not have the same number of replicates per donor per treatment, and we consider this value R star, which is the sum of the replicates, the total number of replicates skin sections that we have for the reference distribution, and we are going to use this value R star to evaluate the within reference variability, as we see here. Additionally, we're going to use a linear model to estimate the point estimate, or GMR, and its standard error, as we see here. This linear model has the donor and the treatment as factors. So in the case that the SWR is less than the cutoff point, we are going to construct a confidence interval for the difference of the means of test minus reference. Whereas in the case of this SWR value being greater than the cutoff point, we're going to test the scale hypothesis. We have the scale criterion, and we're going to observe the upper 95% bound of the scale confidence interval. If this is less than or equal to 0, then the null hypothesis will be rejected, and rejection of the null hypothesis supports bioequivalence. This criterion is a mixed criterion because it is accompanied by a point estimate constraint. So it requires the geometric mean ratio, or the point estimate, to be contained within the limits 0.80 to 1.25. Now, what happens with the case of outliers, when we have outliers? So here, the nature of an outlying observation in this setup will be a within donor extreme replicate value. Is it meaningful to consider outlying donors? Now, we will take a look at a picture again in a moment. So here also we have standard practices that have been used for pharmacokinetic studies, such as standardized residuals, that do not apply in this case because of the small sample size of replicate values per donor. How do we can use the results from Dean-Dixon tests? How do these results compare to using another test for identification of outliers, such as the GRABS test? Such tests are appropriate in this case because of the small sample size. So here we have cases of experimental conduct anomalies that are detected once the sample analysis is completed. So let's take a closer look at the graph, the matrix that we saw previously with the flux profiles. So here we notice, as we said, that we have a consistent behavior of one donor across products. So we have 4 donors for each different column and 2 different formulations. Each row is a different formulation. So we have a consistent behavior for one donor, but we may have one replicate or more than one replicate skin section that is behaving differently than the others. And an example here is for the 4th donor, and the first formulation, we have the blue profile being extreme, right, comparing to the rest. So here is an example of having a data set with 20 donors and having outlying replicate values. And a similar example can be seen here with another data set with 15 donors. So we have here 2 categories for the 2 products, reference and test. Other questions that arise are what is, for example, the impact of varying the alpha value, the significance level value, on the number of identified outliers using a fixed test, here the Dean-Dixon test. So, of course, we expect the number of identified outliers to vary when we vary the alpha value. So here, for example, we have examined 3 different alpha values, 1%, 5%, and 10%, and for each of the reference and test formulation, and in every case using the Dean-Dixon test. And we see that, of course, when we have 1% alpha, we have more outliers than when we have 10% alpha. What is the impact of changing the alpha value and selecting a specific outlier test on the estimated geometric mean ratio, or on the point estimate? So here we're considering still the 3 different alpha values, but we also consider 2 different tests, the Dixon test and the GRABS test, and also a case when the outliers are all included in the data set. So in the first two cases, we exclude the outliers identified by the Dixon test, we exclude the outliers identified by the Grabs test, or we include the outliers, and we notice that we have no impact on the estimated value of the GMR. Additionally, we want to see what the impact of changing alpha is and selecting a specific outlier test on the upper bound of the scaled confidence interval, the upper 95% bound. So here we have the same setup with the same three values of alpha, 1%, 5%, and 10%, using the Dean-Dixon test, the Grabs test, and including all the outliers. So in this case, we see that for the case when we exclude the outliers, there's no difference between the Dean and Dixon test versus the Grabs test. Whereas when we include the outliers, we have a remarkably lower value for the upper bound of the confidence interval. This is expected, or this is reasonable, because when we include the outliers, we expect to have higher variability. And when we have higher variability, we're going to have a higher amount of scaling. So the upper bound will tend to be lower. As a conclusion, we could say that varying the alpha value within a specific outlier test seems to affect the number of outliers identified. However, the impact of a combination of the choice of a specific type of outlier test and the changes on the alpha value does not seem to be significant based on the data from the different IVPT studies that we have examined. We note, however, that the results are only based on the limited availability of data that we have for these IVPT studies, and we need to further investigate the potential impact of outliers. So we need more applications, more such data sets, and simulated data sets based on them. So here, to further observe or investigate the impact of outliers under different scenarios, we have considered one scenario where we have a low value of FWR, which would prompt us to using the non-scaled approach, and also a value of GMR, which is 1.3. So it would be outside the range of 0.80 to 1.25. So we have use the simulation study to observe what is happening, what is the impact on the passing rate, the passing bioequivalence rate, the proportion of time that the scaled approach is used, the proportion of proportion of time where the upper bound of the scaled confidence interval would be less than or equal to 0, and the proportion that the point estimate is contained within 0.80 to 1.25. Here, the two curves, and apologies for this not being very clearly seen, but I tried to include all pictures in one slide so we would be able to make comparisons. Here, the case of when we see the green curve is the case when we have the outliers being excluded from the data, whereas the blue curve is when outliers are included. So in the first case, for the passing rate, we see that we have a very low passing rate given both scenarios, including or excluding outliers, but we have a slightly higher passing rate with including outliers. We have a dramatically increased proportion of time when we use the scaled approach when the outliers are included. And as mentioned earlier, this is, we expected that, or this is reasonable. Also, we have a higher proportion of time when the scaled upper bound is less than 0. So this is again similar to the previous result. However, the point estimate remains stable under both scenarios of including and excluding outliers. A similar situation, or we applied a similar simulation study, having now a different scenario. Everything else remains the same GMR, but now SWR is 0.4, so it is higher than the cutoff point, and that would prompt to using the scale approach. So here that we notice that the passing rate is pretty much stable under both situations of including or excluding outliers. And same thing happens with a proportion of time of using the scaled approach. Of course, here it is 100%, because as we said, we were simulating from a data set where we have a high value for SWR. The proportion of time that the upper bound of the scale confidence interval is less than 0 increases when the outliers are included in the data set. But again, the proportion of time that the point estimate is contained within the limits remains stable here. So concluding here, we can say that our simulation study shows that including outliers does not necessarily make a study easier to pass bioequivalence, as long as SWR is greater than 0.294 in both cases of including and excluding outliers, and that the point estimate is not affected by including or excluding outliers. I would like to also add here that for all these simulation studies that I showed, we assume that the outliers are coming in an approximately balanced way from both the test and the reference distribution. And our research has shown that the results change when we have outliers coming primarily from the test or the reference distribution. So finally, I would like to show some references and acknowledge my colleagues for all their help and guidance. And thank you for your attention.